There is a fundamental difference between memorizing the answer key and actually learning the subject. The student who memorizes gets 100% on the practice test but fails in the real exam because the questions changed. The grandmaster learns the principle and wins every time. If your neural network is crushing it in your Jupyter notebook but failing in production, it's not learning, it's cheating. Today, we are going to learn the mathematical art of forcing your AI to be honest. This is a masterclass on regularization. What's up everyone? Welcome back to Sumantra Codes. I'm Sumantra. I have spent years engineering machine learning systems, and the number one thing that separates a junior data scientist from a senior ML engineer is not how complex their model is. It is how robust their model is. Anyone can fit a curve to a set of points. That's easy. The hard part is building a model that understands the underlying laws of the universe that created those points, rather than just connecting the dots. Today, we aren't just skimming the surface of dropout prevents overfitting. We are going to derive the geometry of L1, L2 regularization. We are going to debunk the myth that weight decay and L2 are the same thing. Spoiler alert, if you are using the Adam optimizer, they are not, and it's ruining your model. And we'll visualize exactly why dropout is mathematically equivalent to training an ensemble of exponentially many neural networks. If you're ready to stop building fragile code and start engineering intelligence, grab your coffee and let's dive in. Let's start with a philosophical problem that plagues every single machine learning model, the ill-posed problem. Imagine I give you 7 dots on a graph and ask you to draw a line through them. Mathematically, there are finite lines that can pass through these 7 dots. I can draw a straight line that misses a few. I can draw a smooth curve, or I can draw a chaotic squiggly mess that hits every single dot with zero error. If we only optimize for accuracy or minimizing loss, the math prefers the squiggly line. It has zero error. Ideally, the loss function j theta is 0, but we know intuitively that this line is garbage. It is reacting to noise, not signal. So how do we tell a computer which only understands numbers that simple is better? We have to introduce a constraint. We need to change the goal of the model. Instead of just minimize the error, we update the equation to minimize j theta plus lambda r theta, or we change it to minimize the error plus the complexity. This extra term, r theta, is our regularization term, and the lambda is the knob we turn to decide how much we care about simplicity. If lambda is 0, we get the squiggly line, or we are overfitting it. If lambda is huge, we get a flat horizontal line and we are underfitting. We are looking for the Goldilocks zone. We are going to penalize the model for being smart in the wrong way. We are going to punish it for having large weights. Why large weights? Because large weights mean the model is screaming. It means a tiny change in input x causes a massive swing in the output y. That is instability. We want the model that whispers. Let's look at the few major techniques. First, L1 regularization, also known as Lasso regression. The formula is r theta is equal to sum of absolute value of weight of each item. In L1, the penalty is the sum of absolute value of the weights. It seems simple, right? Just add up the magnitude of the weights. But this technique has a superpower that makes it unique, and which is sparsity. L1 regularization loves zeros. It aggressively tries to turn your weight into exactly 0 if you have a data set with 1,000 features, but only 10 of them are actually important. For example, predicting cancer risk from a generic DNA markers. L1 will identify the 990 useless features and effectively delete them by setting their weights to 0. But why? Why does L1 creates 0 while other methods don't? To understand this, we need to look at the gradient. Think about how gradient descent works. We update the weights based on the slope or derivative of the loss. The derivative of absolute value of w is either +1 or -1. It is a constant force. Whether the weight is 1 million or 0.0001, the L1 penalty pushes it towards 0 with the exact same strength. It's like bulldozer. It pushes the weight all the way to the origin and traps it there. Visually, look at this. The geometric shape L1 is a diamond or a cross polytope in higher dimension. When the loss function, these ellipses, expand to find the minimum, it is statistically highly probable that it will hit the pointy corners of the diamond first. Where are the corners of diamond? They are on the axis, and on the axis, the value of the other weight is 0. So what is the practical takeaway? When do you use L1? You use it when you suspect sparse features. If you're doing NLP with bag of words, where most words don't appear in the document, or a gene selection, L1 is your best friend. It performs automatic feature selection for you. It simplifies your model by killing the dead weight. Now let's talk about the industry standard, the default L2 regularization or ridge regression. The formula is r theta is equal to sum of the square roots of all the weights. In L2, we penalize square of the weights. So loss is equal to error plus lambda sum of w square. This sounds like a small change, but the behavior is completely different. Let's look at the derivative again. What is the derivative of w square? It's 2w. This is crucial. The force that L2 exert on the weight is proportional to the size of the weight. If the weight is huge, e.g. 100, the gradient is 200. The penalty scream shrink down. If the weight is tiny, e.g. 0.01, the gradient is 0.02. The penalty whispers, you're fine. Because the force fades away as you get closer to the 0, the L2 regularization never actually pushes weights to exactly 0. It just makes them really small. It diffuses the signal. Instead of having one massive weight of 100, L2 prefers to have 10 weights of 10. It spread the blame across all features. Geometrically, L2 defines a circle or hypersphere. The loss function touches the circle at a tangent point. Since a circle is smooth and has no corners, the intersection point is almost never on the axis. This means you keep all your features, but they all are constrained. So what is the practical takeaway, and when do you use L2? Almost always. If you are dealing with images or pixels, audio, or dense data where every input correlates with the output, L2 is superior. It prevents any single neuron from dominating the network. It prevents the exploding gradient problem. It keeps the model stable. Okay, stop what you're doing. Listen to me very closely. If you're using PyTorch or TensorFlow and you're using the Adam optimizer, which is 90% of you are, you're likely implementing regularization incorrectly. For decades, we taught that L2 regularization and weight decay are the same thing. Mathematically, in standard stochastic gradient descent, they are the same, which is W new is equal to W old minus learning underscore rate multiplied by gradient plus lambda into W old. You can fold the penalty into the gradient or apply it to the weight directly. It is the same math. Adam is an adaptive optimizer. It scales the learning rate based on the history of the gradients or variance. If you add the L2 penalty into the gradients, which is how standard L2 works, Adam ends up normalizing it. Adam looks at the penalty and says, oh, this is just a part of the gradient and let me scale it down. It effectively weakens your regularization. You set lambda to 0.01, but Adam treats it like lambda is equal to 0.0001. This was a huge mystery in deep learning until 2017 when a paper by Loshilov and Hutter proved that L2 regularization in Adam is broken. The solution is AdamW. The W stands for weight decay decoupled. In AdamW, we do not add the penalty to the gradient. We apply the weight decay directly to the weight after the Adam update is calculated. We bypass the adaptive scaling. So what's the lesson? If you're training a transformer, a ResNet, or any modern deep learning model with Adam, do not use Adam. Use AdamW. If you use a standard Adam with weight decay, you're essentially training with no regularization. This simple switch can boost your model generalization by 2 to 5% instantly. Finally, let's talk about the most aggressive, counterintuitive, and effective technique in modern deep learning, which is dropout. Proposed by Geoffrey Hinton, the intuition comes from the corporate management. If you have a team of workers and one person is a genius, everyone else gets lazy. They just wait for a genius to solve the problem. If the genius gets sick, the team fails. The team is not robust. To fix this, management randomly fire 50% of their staff every single day. Don't do this in the real life, please. In Dropout, during every single training step, we flip a coin for every neuron. If the coin gets heads, you stay active, and if it gets tails, you are zeroed out, you're dead. What does this force the network to do? So first, it prevents co-adaptation. Neuron A cannot rely on neuron B correcting its mistakes because neuron B might not be there. Every neuron must be useful independently. And the second one is ensemble effect. This is the mind-blowing part. If you're having network with n neuron, there are 2 to the power n possible subnetworks. Every time you run a batch with dropout, you're training a different subnetwork. Over time, you're effectively training an ensemble of exponentially many different models that share weights. Now a critical implementation detail. If I kill 50% of your neurons during training, the total volume of the signal passing through the network is cut in half. If I test the model and turn all neurons on, the signal will be double what the network expects. It will explode. So we have to scale. In modern libraries like PyTorch, we use inverted dropout. During training, we keep a neuron, we multiply its value by 1 over 1 minus p. If p is 0.5 or 50% dropout, we multiply the survivors by 2. This keeps the magnitude of the signal consistent so that at the test time, we can just run the network normally without doing any math gymnastics. So the takeaway is use dropout in a fully connected network layers of your network. It is arguably the single most effective tool for preventing overfitting in large models. So we have covered the mathematics of constraints, the geometry of high-dimensional spaces, and the specific quirks of modern optimizers. Let's condense this into your cheat sheet. First, L1 or Lasso regularization is for sparsity. It creates diamonds, it pushes weights to 0. Use it when you need to select features and ignore noise. The second one is L2 or ridge regularization. It is used for stability. It creates circles. It keeps weights small and diffuse. This is your default setting for keeping a neural network well behaved. The third is AdamW is king. Do not use standard L2 weight decay with Adam. The math conflicts. Switch your import to torch.optim.adamw and watch your validation loss drop. And the fourth one is dropout is an ensemble. By randomly killing neurons, you train thousands of overlapping subnetworks. It forces independence and robustness. Building a model that gets 100% training accuracy is easy. I can do it in 5 lines of code. Building a model that works on data it has never seen before, that's an engineering. Regularization is the tax we pay on complexity to buy generalization. I want to hear it from you. Have you ever been burned by the Adam versus AdamW bug? Or do you have a specific horror story where L1 regularization deleted a feature you actually needed? Let me know in the comment below. I'm Sumantra. This is Sumantra Codes, and keep engineering intelligence. Thanks.